Alright, so this quarter we're gonna learn stochastic processes. So in chapter 4 we're gonna learn Markov chains, and Markov chain is one type of discrete stochastic processes. So let's first define what a discrete stochastic processes is. Alright, so we have x sub n. And this n is can be 0, 1, 2, 3, etc. up to infinity. And so, and n is like time. Okay. So for example, when n is 0, this is like we start our clock. And now, okay, so, and there is another, so the values of xn can take. So these are called, so for example, so if xn is, say, I, alright? So, and I is in some set S. So this S is called the state space. So it's basically what values this stochastic processes can take. So before we move on to a formal definition, let's see a very, very simple example. Okay. Oops. So we say so we want to determine whether tomorrow will be raining or not. So let's suppose there is only like two states. So let's say if it's gonna rain or if it's not gonna rain. All right. So let's suppose the probability of a given day, given it's raining, and tomorrow, so this is like tomorrow, and here this is today. So for example, this is like 0.4, so which this says given today is raining, there is a 40% of chance tomorrow it's gonna continue to rain. All right, so we draw a small arrow here, so which means, so if today it rains, tomorrow we have 40% of the chance it's gonna rain. And because there are only two states, this means the following. Because given today it rains, tomorrow it's either gonna be raining or sunshine. So what we have here is actually 1 minus this probability. So, and this is 0.6. So this means if we're at this state, which is raining, so it is possible to change to another state with 60% chances. Okay, so similarly, okay, let's consider, so given today, and again, this is today. Okay, so, and here is tomorrow. So given it is today is not raining, and the chance of tomorrow is gonna rain, let's suppose this is 0.1. Okay, so which means if we are at So if we're at the sunshine, this state, not raining, we have 10% chances go back to this raining state. And similarly, so if today we have sunshine and tomorrow, so we have 90% of chance it's still sunshine. So we draw a little arrow, go back to S itself, and this is 0.9. Okay. So now if we assign a value to these states, so for example, so we can say if it rains let's say at time n, so if it rains, xn is 0. So otherwise, if it's sunshine, so xn is 1. Okay. And so now a possible trajectory is, for example, so x0, we have x0 is, let's say it rains today, okay? So then tomorrow, now which is at time 1, so it is, let's say it still rains, and x2 equals 1, which means on day 2, or say at time 2, it stopped raining, and it's not raining, so etc. So this is a stochastic processes. Of course, we can have x0 take another value, so it's all about these 4. So these 4 probabilities, so they are called transition. Oops. So they are called transition probabilities. So now let's formally define this transition probabilities. So it defines as follows. So transition so it is a conditional probability that given x n is I, so this means at time n we are at state I, and x n minus 1 is let's say I sub n minus 1, and etc. up until maybe say x0 is I0, and this one, let's say this is j. So the conditional probability of, so these are known, so these are known. The conditional probability of the future, so this is This is like a future. And this one, so this one is like our present. And all these are like our past. Okay. So if it is, so this is our transition probabilities, and this transition probabilities equals, so let me write down here. Whoops. So it equals Pij. So which means this transition probability only depends on the present state, the current state, which is x sub n. So let me emphasize here. And this depends only on the present x sub n. So, and this, we say, this is a Markov process. And this property is called, so this is called Markov property.